we are in time, so let's start where I left in last class. Um, I was talking about the temperature and heat, and I told you they are different things. Temperature is not important, heat is really important. Yeah, heat is what we really need in our life. Temperature is just a measurement that is used to do some calculations. Everybody got that? So let's look here. So I'm going to write one equation that has not been used yet. So this equation is called heat equation. Q is equals to mc T2 minus T1. So this equation is called heat equation. So this Q is a heat. So Q is called heat, and it is the mass of the substance. This is called specific heat capacity. T2 is at some temperature. T1 is another temperature. Don't worry about this at this point. I just want to tell only one thing here. So M. So look here. So heat depends, the heat energy. Heat energy Q depends on the mass of the substance. Everybody got that? If mass is more, Q is more. Because look here, in this equation, M is in the numerator, Q is also in the numerator. Both are in numerator, right? So if mass is more, heat is more. Everybody got that? So let's say you have a drop of water here. Let's say you have a drop of water here, and it is at, let's say, 100 degrees centigrade. And if you have, let's say, here 5 kg of water, 5 kg of water, so this has temperature, let's say, 25 degrees centigrade. So you look here. So the temperature, so it also depends on the temperature difference, but rather than this, it really depends on this mass factor. Everyone got that? So here mass is how much? 5 kg. So definitely this water has a lot of energy comparing to this 1 gram water. You got that? So even though this guy has 100 degrees centigrade, this has 25 degrees centigrade, there is a lot of mass, right? So this has larger energy compared to this energy. Everyone got that? So mass always has, if you have a bigger mass, even if it's a low temperature, it has a lot of energy. Got it? So you can easily think like this way. Let's say we have a very cold water here in the hill, very cold water. Let's say it's about 5 degrees centigrade water, and it can flow, right? 5 degrees centigrade water is not ice, yeah? So in 5 degrees centigrade, water can flow. Only in, so if you go outside today, that there might be 10 degrees centigrade, and you see ice is melting and the water is flowing, right? So so this water can flow. So maybe here is, let's say, a lot of water here. So let's say this is a 1,000 kg water in a dam here. So here is a, let's say, some water that is 100 degrees centigrade, and this is 1 kilogram, 1 kilogram. So which water has more energy, this water or this water? So you can simply think that, okay, I want to open this valve here and make a electricity here. So from so this is a basically magnet. So if you put a fan here to rotate it, this 1,000 kg of water can rotate this turbine long time, giving you a lot of electricity here, right? 1,000 kg is a lot of water. Make sense? So, but look here, there is just 1 kg water. Just do the same thing here. Put a very big magnet here like that. So 1 kg water, here is a fan, and this 1 kg water even cannot rotate this magnet here. So this has very tiny amount of energy. If you got that, it's very simple to think which has more energy. So if you have a lot of water, even if low temperature, that has a lot of energy stored in it, and it can do really a lot of work. Make sense? So, but here, look here, a small amount of water, too hot, but it really cannot do any work because it's very small, and when you flow it, it doesn't rotate anything. Everyone got that? So it's that simple. So rather than temperature, it's really the mass, the energy depends on it. Yeah. So if you have a more mass, you have more energy. Got it? Good. So now we need to talk about the how do thermodynamics is studied is that there are some terms we need to define this term first before we study thermodynamics. So I want to study about this. Let's say here is a beaker or cup, you can say, and we have water here. So it's water here. If you want to just study what happens to this water, yeah, so you just want to study about the water, then that becomes your system. What you want to study is called your system. Make sense? So if you want to study water and this cup together, that becomes your system. You got it? So whatever you want to study here, that is called your system. So maybe this is a hot water and maybe some vapor is going up like this way. So let's say you want to study only that vapor, only that vapor. So if you just want to study what is going on this vapor, that becomes your system. Make sense? What you want to study is your system. So let's say, all right, so I want to study what happens here in heat-wise. So I want to study water and vapor together. So this becomes your system. Yeah. So you are studying vapor and water together. So that's your system. You might say, okay, I just want to study. I don't care about this, what is going on this vapor, but I just want to study this liquid water here. So this becomes your system. Make sense? So you might say, all right, I'm very expert on everything and I want to study together this vapor, this water and this beaker material here. So this becomes your system. So basically whatever you want to study in thermodynamics, that is called the system. Make sense? So I want to study about him. So he becomes the system and everything around here is surrounding. Yeah. So let's say I want to study about what happens if I connect this cell phone in the wall. So what happens to this, how much heat it flow here and what is the temperature of this cell phone would be. So if I want to study something like that, my cell phone is a system. Got it? So whatever you want to study, that is called system. So I'm only studying my cell phone. So except my cell phone, what is around here, that is called surrounding. Make sense? So I want to study about this cell phone. So this is a system. Outside this cell phone, what is everything around here, that is called surrounding. And the surrounding and system is separated by a thin imaginary line that is called the boundary. Make sense? So like that. So let's say that, look here. So I just draw again this a cup of water here. So it's vaporizing probably. So I just want to study the liquid water here. So liquid water here. So this liquid water is my system now. This is system. And so this thin line here that I am drawing, that is called boundary. B-O-U-N-D-A-R-Y, boundary. And this vapor, this glass material and outside air, whatever here, they are called surrounding. You got it? Easy? So let's look about this duster. So I want to study about this duster here. So this duster, if I give some heat, what happens? What is the temperature? What will be the temperature difference here? How much heat it will be absorbing? How much heat it will be losing? Something like that. So this become my system. And I just imagine a very thin line here, like that. That is called the boundary. And everything what is around here, that is called the surrounding. Yeah. Everyone got that? So it's pretty easy. So how about this one? So this is a bottle here. I just want to heat this water and just want to study about the water inside, right? Only water. So that's the system. And this bottle and everything outside is called surrounding. And just imagine a line. There is a line between that water and this wall of this bottle, and that is called the surrounding. Just imagine, yeah? You cannot make a wall between this water and the bottle, right? So we just want to imagine that, yeah? So that is called the boundary. Everybody got that? So some definition, yeah? There are some definition in homework. So I just give some example and tell you which one is the system, which one is the surrounding, and which one is the boundary, yeah? Good. So whatever you want to study is the system. The system and surrounding is separated by a thin imaginary line. That's called boundary. And outside the boundary, what is there is called the surrounding, right? Easy. Now, so let's go and look some types of system here. TYPES, types of system. Types of system. So it's basically like this. This is the water bottle, right? Now, If I tightly close this, the water cannot go outside, right? Look at, there is no hole. I tightly plug this one, so mass is not being lost. So water molecule is not going out, right? So mass is not lost. So open, so closed system. Let's start with the open system. So if this is the, if I open the bottle like this is open here, right? So water vapor can easily evaporate. Water can easily evaporate it, go out, right? So if I put it here, so probably tomorrow I come here, all the water is gone by evaporation method. Make sense? So the mass is being lost continuously. So if mass is being lost, mass is equivalent to energy. If you talk about the mass is the energy. There is no difference between energy and mass in physics, chemistry, or engineering. If you think about mass, it's immediately the energy. Make sense? So if mass is being lost, energy is being lost. So in this case, so open system. So open system is open system. So open system is this is the system. Mass is lost from the system. So when the mass is lost, energy is also lost. So both things is being lost, right? So mass is being lost, energy is being lost. So this kind of system is called open system. Make sense? So what is the definition? What is the example? So let's say you have a cup of tea here. So cup of water or cup of tea. So this is the open system. Open system. So why it is open system? It's the open here. So continuously water vapor is going out, right? So mass is being lost. So mass is being lost. The energy is also being lost. Make sense? Everyone got that? So let's talk about the closed system. So I'm going to write the closed system here. Closed system. Closed system. So it's just like the make this water very hot, yeah. So heat the water and fill in the bottle and cap it like this tightly. So it's very hot now, right? So I just heated it and it's very hot. Put it here. So tomorrow you come here and look this one. The water is not lost because I'm just tightly cap it, right? So water cannot go out. But today is very hot. Tomorrow when you come and fill it, it will be very cold, meaning that it lost the heat, but it didn't lose the mass. Make sense? Everybody got that? So this is like the closed system. So closed system is just take a hot water in a bottle and tightly cap it. So the mass cannot be lost. So here mass cannot be lost. Mass is not being lost. Mass can go out or come in, whatever you want to say. Mass can't be lost. Can't be lost from this system. You got it? Because it's tightly closed, right? But what happens? Does it become cold? Yes, it becomes cold. So heat it, tightly close it. So hot water, then just put outside in the snow or outside, and tomorrow just toss this water. It will be very, very cold. So where does that heat go? From the wall, that heat goes out to the snow. Make sense? So it loses the heat. So lost the heat. So both things are lost. Mass can't be lost because it's tightly closed here. So mass cannot go out, but it lost the heat because from the wall of this container, so the heat is going out like that to the environment. Make sense? So this is the closed system. Now let's talk about the isolated system. So isolated system. Isolated system. So isolated system. So it is a thermoflask basically. Thermoflask, right? So you in the morning you cook your food and put in the thermoflask, and you want to eat in the office in the evening, and it is still hot, right? It's not becoming cold. Make sense? So it is not losing heat. It is not losing the mass. Yeah. So take a thermoflask here. So this is a thermoflask. So thermoflask here. So thermoflask is like this, and they have the very thick wall here. So multiple wall they put like that. Yeah. So go to home and look here. The thermoflask has a really thick wall like this, and also they put some kind of the rubber or the wood here to close it. So they put some material here, hot material. So you put this material in the morning here, hot material. So you want to eat in the evening, and still this is hot. So it is not losing heat or not gaining heat. So this is mass is not lost. Mass is not lost. Why? Because there is no hole and you just tightly cap this. Mass is not lost and heat is also not lost. Heat or energy, heat is not lost. So heat doesn't come in, heat doesn't go out. A mass doesn't come in, mass doesn't go out. Make sense? So this kind of system is called isolated system. It's clear? Good. So open cup, a cup that has water. So water evaporates easily. Open system. Like the bottle, it tightly cap it. The heat doesn't go out. Heat go out, but mass doesn't go because you capped it, right? So that's a closed system. And something like this, the thermoflask is a isolated system because mass is not going out, mass is not coming in, heat is not going out, heat is not coming in. So it's just warm. Yeah. So that's called isolated system. Good. So types of system. All right. So I give the example there. And here is a problem from our book. So the book says this problem is, suppose we are studying the reaction occurring in a beaker on a table in the laboratory. What constitutes the surrounding? So it is saying that, so you have a table here in the lab table, and in that table you have the beaker here, and you are studying some reaction here. So what constitutes the surrounding, right? What constitutes the surrounding? So I want to think this water is a system. This is my system here. This reaction mixer. So whatever the chemical is there and whatever the water is there, that's my system, right? So the surrounding would be, so this beaker, so this beaker part and this table part and whatever outside in this room and the room. All this is surrounding. Make sense? So what is the system? System is just this water where I am studying what happens, how much temperature will change, how much heat it will absorb, something like that, right? So when this is system, this beaker, I'm not concerned, this table, I'm not concerned, the outside room, I'm not concerned, right? So that's my surrounding. Everybody got that? So only just that mixer, what I'm studying, that's the system, and every other thing is surrounding. So this is saying the universe, which are the contents of the beaker, is called the surrounding. So basically they call this as a universe. So they call it everything is a universe. Everything is a universe. So if I am talking about this room, they in thermodynamics, they talk this room as a universe. Yeah. So this room is a universe. So we are just, so this is a table. So I have this reaction, I'm doing reaction there. I put thermometer there, looking the temperature here. So only that water, the reaction mixer is the, that part is my system. Everything containing this bottle, everything is a surrounding. Make sense? So they call the word the universe. Yeah. So everything is called the universe. Make sense? Good. So thermodynamics, it's very confusing actually because of these too many terminology and sign convention. So now let's talk about the energy transfer and symbol. Energy transfer, transfer, and sign, S-I-G-N-S, signs. So let's say you have this heater. So this is a heater, right? So oven, heater. So you put a cup of cold water here. So when you do the heater on, the heat will go from oven to heater, right? Like this way. Make sense? So that the water becomes hot. So in this case, water is absorbing the heat from the oven, right? So that heat is called plus. So we get that Q, the heat, how much heat it is absorbing from heater to water here. So water is taking heat from heater. So that is called, given as a plus sign. Make sense? Plus sign. So if something becoming hot, that's a plus. Make sense? So if you think this class, I'm talking and you are observing, right? So I am minus, you are a plus. Because you are observing, I am giving. Everybody got that? So this guy, water, our system is taking heat. So the heat is given as plus. Now let's do another one here. So let's say I have a water here. I have hot water here, hot water, and I put this water in ice here. So this is ice. So heat goes from where to where? From here to here, right? From hot to cold. So heat goes down here from my system to the ice. So In this case, if this water is losing heat, so I give that as a negative sign. Make sense? It's just like the money. Thermodynamics is much more similar to money. If I get money, I am plus. If I give out money, I am minus, right? Just like everybody got that? Easy, yeah. If somebody comes from outside here, our class become plus. If somebody goes out from here, our class become minus. Yeah. So somebody is heat here. Make sense? So if heat is coming from inside to here, our system is becoming plus. And if heat is going from here to out, our system becomes minus. Minus. Everybody got that? Good. So if the heat is being lost, it is minus. We give the minus sign to that amount of heat. If the heat is coming in to the system, we give the plus sign to that heat. So basically, I am giving two cylinders here. It is nothing other than water in the cup, yeah, or the gas in the cylinder. Make sense? So now let's talk about thermal equilibrium. Thermal equilibrium. You already know about this equilibrium term. Equilibrium means equal, right? Equilibrium. So equilibrium means equal. Thermal means temperature. Make sense? Thermal equilibrium means temperature equal. So I have two things here. So let's say it's a iron block. So this is iron block. So iron. So it's made up of iron, and it's also, let's say, iron or copper. You can say anything. This is another iron. So let's say it is at 60 degrees centigrade and it is at 25 degrees centigrade. So if I connect this with a wire, the heat will flow from this high temperature body to low temperature body. Make sense? Until when that both the temperature becomes same. So maybe this is 60 at let's say 20 degrees centigrade here. So this is 60, this is 20. It's like that. Now the temperature of both will be approximately 40 degrees centigrade. So heat will go from here to here until this also becomes 40, this also becomes 40, average temperature. Make sense? So this is called thermal equilibrium. So if a hot body and cold body are connected by a wire or they are in contact, the heat will flow from hot body to cold body until the temperature of both become same. Make sense? So I just connected it. So after the connection, and I wait for a while, and it becomes like this. So this is this one, this is another body here. So like this. So this also becomes 40 degrees centigrade. This also becomes 40 degrees centigrade. So if you put the thermometer at the beginning here, it was showing 60. Put the thermometer here at the beginning showing 20. So after a while, maybe you just connected it for a while, and then you see here. So this also showing 40. This also showing 40. Everyone got that? Yes? So that's called thermal equilibrium. When two bodies have same temperature, heat does not flow, right? From one to another. So it only flows from high temperature to low temperature. So when the temperature of two objects becomes same, it does not flow, and that condition is called thermal equilibrium. Temperature equal. I'm not saying the heat equal, it's a temperature equal, yeah? Good? Like that. Good. Thermal equilibrium. Now, so when two bodies are in thermal equilibrium, the heat does not flow. Now, exothermic and endothermic process. So let's talk about exothermic process. So it is very important for our lab next week after the spring break. Exothermic and endothermic process. Endothermic process. So let's say you have a water here. This is a water, and you throw some sodium hydroxide in this one. You throw, let's say you have a thermometer here. At the beginning, you have, let's say, 25 degrees centigrade here, and then throw some sodium hydroxide here from outside. The temperature becomes, let's say, 80 degrees centigrade. You see that? So heat is given out by that reaction. Therefore, the water becomes hot, right? Exothermic means heat is given out by the process. So what I did, so there was water. At the beginning, I record the temperature at 25 degrees centigrade, right? And I throw some of the sodium hydroxide in this water here. And immediately after I throw the sodium hydroxide here, the temperature increases and become 80 degrees centigrade. Where does that temperature rise? Because of the heat given by that reaction. Make sense? So this kind of the process is called exothermic process. So you can touch at the beginning. So take a water here, touch it, it feels cold, and throw some sodium hydroxide here and let the reaction be, and then touch it again, you will feel hot here. So this becomes, the system becomes hot. Yeah. So it is the process where that process gives some heat and the system becomes hot. The temperature rises, right? So that's called the exothermic process. Got it? Exothermic. Now let's look at the endothermic process. So in exothermic process, system becomes hot. Endothermic process, system becomes cold, right? Cold. So let's look here. Heat is absorbed in the process. So let's say you have some water here. You have some water here. Put the thermometer here. Let's say it's about 25 degrees centigrade. Now throw some ammonium chloride here. Ammonium chloride is NH4Cl. Ammonium chloride, and the temperature goes down to 21 degrees centigrade here. System become cold, right? So ammonium chloride I put in water, and the whole system become cold, right? So this kind of process is called endothermic process. Make sense? So I just put the thermometer there and do something in that mixer, and if the temperature goes up in that thermometer, the system is exothermic, and if the temperature goes down, that system is endothermic. Yeah. Everybody got that? Just like that. Good. So another is ice absorbs heat and melts. So that's also endothermic process. So in the lab, we will be mixing some sodium hydroxide and water, and we will see the temperature rise. Yeah. So this is called exothermic and endothermic process. So you put some fuel in your car, and then you burn it, and the engine become hot, right? Engine become hot. If the engine become hot, it cannot work, right? So the burning of fuel is also exothermic process. Good. Now energy. So if you look your energy bill, probably you don't see your energy bill. If you have a home, probably you are doing, but if you have an apartment, you probably don't see your energy bill. So the energy bills are written like this, joule, in terms of joule. So they write how many joule of heat energy you used this month, or how many joule of electric energy you used this month, right? The company send the bill. Sometimes they report in the joule or kilojoule, or sometimes they report in the watt hour or kilowatt hour. So the kilowatt hour, so something like that. Yeah. So this is the energy unit. Make sense? So like the electricity company, how do they do the calculation? So they have some unit to calculate. So 1 unit, 2 unit, 3 unit, 4 unit electricity, something like this. So the unit of energy is joule, J-O-U-L-E, joule. The unit of energy is joule, and it is written as J, joule. So if you are talking about 1,000 joule, so 1,000 joule is 1 kilojoule. Make sense? Just like 1 meter, 1,000 meter is equal to 1 kilometer, right? 1,000 milliliter is equals to 1 liter. Just like that, 1,000 joule is equals to 1 kilojoule. Make sense? Just like that. So there is another unit. They call that unit as a calorie. Most of the food energy is written in calorie. Yeah, food energy. Like if you go to Quick Trip and buy a soda of 250 ml soda, like the Coca-Cola, and they write there 140 calorie here. So food is most of the time is expressed in food energy, is expressed in calorie. Make sense? So you can just look the bottle of the drinks, the pack of the packed food, like the chips and whatever. Just look there, and they write there how many calorie of energy is there. Yeah. So calorie. So what is the relationship? How much is the factor to convert joule to calories? So basically, 1 calorie is equals to 4.184 joule. See that 1 calorie is equals to 4.184 joule. So I'm going to show you one example here. So you have a soda here. You have a soda. soda, and the soda, in the label of the soda, they write 140 calorie. So how much in the joule? So I want to convert in this calorie into joule, yeah? So how much joule energy here if I'm saying 140 calories? So so they are saying 140 calorie. I want to convert that into joule. So I don't need calories. So I put the calorie part down and I put the joule part of 4.184 joule part of calorie cancel. So 140 multiplied by 4. So comes to be 16, 556. So it's about 560 joule of energy. You see that? So 140 calorie is approximately 560 joule. So sometimes people might say, oh, I have 140 calorie. I eat 140 calorie. Or other people say, I eat 560 joule, right? But these two things are the same thing. Saying the same thing in different way. Make sense? It's just like saying the same thing. Sometimes we say, oh, I have a 1 kilogram, or I have a 2.15 pound. So 2.15 pound and 1 kilogram are same. Everyone got that? Is it clear? Yeah, saying the same thing in different units. So I put one problem here. Convert 3.75 10 to the power 3 calorie into joules. So let's convert that into joules. So here is a problem. Convert 3.75 10 to the power 3 calorie. Calorie is given into joule. So I don't need this calorie. I put this calorie down, and I need joule. So I put the joule factor of 4.184 joule factor of calorie cancel. Put this number in calculator and calculate it what comes. You got it? It's pretty simple conversion, right? So good. Now I am in the slide number 14. So here we have a specific heat capacity. So this is very, very important. Specific heat capacity. Specific heat capacity. So specific. So what is specific heat capacity? So specific heat capacity is like this. So take 1 gram or 1 kg. One, not different. Yeah. Take, let's say, so I'm taking 1 gram. So how much water I put here? 1 gram material. So if you are talking about water, take 1 gram water, not other. Not 2 gram, not 5 gram, not 3 gram, not any other gram. Just take 1 gram water. Yeah. Take 1 gram water, and let's say the temperature, measure the temperature, put a thermometer here, and the thermometer is 21 degrees centigrade. So we already know in the laboratory how to measure the temperature of water, right? In lab 1 and other 21 degrees centigrade. Now put this guy. So how much water I put here? Mass, how much? 1 gram. And what is the temperature of initial temperature I have? 21 degrees centigrade. 21 degrees centigrade. Now put this in oven. Put this in oven, and you start to heat it. So until the thermometer shows you 22 degrees centigrade, just 21 degrees centigrade difference. Make sense? So T2 is 22 degrees centigrade. So how much heat it absorbs from oven in this process? That amount of heat is called specific heat capacity. Everyone got that? So how much water you should get? 1 gram. And what is the temperature of that water? Could be 21, could be 22, could be 23, one temperature, right? Maybe 21, and then put in heater and heat it until the temperature just increase by 1 degree centigrade. Here is 21, I heat until 22. Make sense? Just by 1 degree centigrade. And how much heat is absorbed in this process? That amount of heat is called specific heat capacity. Make sense? So basically, it's the amount of heat absorbed by how much? Absorbed by what? 1 gram. 1 gram. I just put 1 gram water there, right? 1 gram material to do what? To change the temperature from 21 to 22 is 1 degree centigrade, right? Just 1 degree centigrade. Amount of heat absorbed by 1 gram mass to change temperature by 1 degree centigrade from 21 to 22. Everybody got that? So 1, 1, 1. So you have to take 1 gram material, put it in the oven, measure the temperature. If it is 25, you need to heat until 26. if it is 30, you just heat that until 31, right? Just by 1 degree centigrade. So how much heat is being absorbed in this process? That amount of heat is called specific heat capacity. Specific means individual, yeah, by 1 gram, 1%. So not everybody, just by 1, yeah. You got it? Like that. So if you have a 1 gram water, so let's say you have 1 gram water, 1 gram water. So if you have 1 gram water at certain temperature, so you want to heat it to just increase the temperature by 1 degree centigrade. In that process, it will absorb 4.2 joule heat energy. Make sense? So let's say you have 1 gram water here, 1 gram water. Let's say it's at 21 degree centigrade. Now you put this in oven, and then the temperature becomes from 21 to 22. So how much heat it absorbs from to go from 21 to 22 is 4.2 joule. Yeah. So if you supply 4.2 joule of heat energy to 1 gram water, its temperature just changes by 1 degree centigrade. Make sense? Did I make it clear? 111. So 1 gram water, it's at certain temperature, maybe 25, maybe 21, maybe 30. I don't know at what temperature. From if it is at 30, I just supply some heat so that the temperature becomes 31, and I calculate the heat. That amount of heat is 4.1. Got it? Like that. Good. So 4 points. So specific heat capacity of water is 4.2 joule per gram per degree centigrade. So how do we read it? So 1 gram of water need 4.2 joule of heat energy to change its temperature by 1 degree centigrade. That's how we read this. Yeah. Make sense? So they write like this. So specific heat capacity of water C is equals to 4.2 joule per gram per degree centigrade. They write like that way. So that means I take 1 gram of water to change the temperature of it by 1 degree centigrade. So I need to supply 4.2 joule heat energy there. That's how we read it. Yeah. Good. Alrighty. So this is specific heat capacity. Now, what is the heat capacity? So if I just erase that specific term, it just becomes the heat capacity, right? Now we don't need to take 1 gram, and we don't take that 1 gram material. Amount of heat required to increase the capacity of a given material by 1 Kelvin. So I might take a lot of material here, maybe 50 gram, not 1 gram. I'm not talking about 1 gram now, right? When I was talking about the specific, I was taking 1 gram, right? But when just I'm talking about the heat capacity, so I take a lot of water or whatever material here, and let's say at the beginning, this is at 21 degree centigrade. Now I heat it to make it to 22 degree centigrade, and how much heat it absorbs in this process, that is called the heat capacity. Specific means you are talking about one guy, but when you got the specific and it becomes the heat capacity, we are talking about all the mass. Make sense? Any mass. So heat capacity is not important. Specific heat capacity is important here because we need to know the value of 1. Yeah. So that 4.2 is important. So let's look here. So let's look here some specific heat capacity of aluminum. So this is aluminum. Specific heat capacity is 0.897 joule per gram per Kelvin. So sometimes they write in per Kelvin, sometimes they write in degree centigrade. Is the same value, yeah. To change something by 1 degree centigrade or 1 degree Kelvin is the same thing, yeah. Sometimes you might see degree centigrade here. Sometimes you see the Kelvin here. It's the same thing. So Kelvin, yeah. Sometimes we express in Kelvin. Sometimes we express in degree centigrade. Is the same thing. So aluminum is 0.897. Iron. So this is iron is 0. The specific capacity of iron is 0.449. And let's say water. So water is 4. Liquid water is 4.186. 4.18, approximately 4.2. So 4.184 is 4.2. And let's take last one, a glass. So last one is a glass. The specific capacity of the glass is 0.8. Look here. So if you take 1 gram of water, you really have to give a lot of heat to change its temperature by 1 degree centigrade. You see that? 4.20. Yeah. So we take what we are doing here. We are taking 1 gram of each substance, and we are trying to change the temperature of that guy by 1 Kelvin. And how much heat we are giving to do that? To change that temperature of 1 gram aluminum, we need to give this much heat, 0.8, but 0.89. But to change the temperature of 1 gram water by 1 Kelvin, we need to give 4.2 joule of heat. So water really takes a lot of heat to get heated. Make sense? So if you are trying to heat iron versus water, so let's say you have iron here and you have water here. You have water here. So let's say iron is also 4 gram. Let's say iron is also 1 kg. Water is also 1 kg. So let's say this is also 21 degrees centigrade. This is also 21 degrees centigrade. So if you are trying to heat this to 100 degrees centigrade, you keep heating and keep heating and keep heating. You keep burning a lot of fuel here to change this water to 100 degrees centigrade. Make sense? But this guy doesn't take that much heat. So burn a little bit of heat here, it immediately convert to 100 degrees centigrade here. Make sense? So if something has a high specific heat capacity, it takes a lot of fuel to get heat, to heat it. Make sense? But if it has a low specific capacity, it becomes hot immediately. Make sense? So if you go to the beach in the summer and then you put your foot in sand, it's very hot. It feels very hot, right? But you put your feet in the water, it still is a cold, right? So water doesn't get heated easily because it has a lot of specific heat capacity is 4.2. So water takes really high amount of heat from sun to get heated. But sand is like the glass. Sand is basically the glass. So the sand get hot very easily because its specific capacity is very low. Make sense? So if it has a specific heat capacity small, it becomes hot very fast. If it has a specific heat capacity very large, it doesn't become hot fast. It takes long time to get hot, become hot. Make sense? So the easiest example is go to the beach and put your feet in water and the hot summer day, go to the beach here and here is the sand and here is water. Put your foot here, it's very hot. Why it's very hot? Because its specific heat capacity is very small, about 0.8, that glass. And the specific capacity of water is 4.2 here. So it doesn't become hot easily. So it becomes hot very quickly. Yeah? Make sense? So like that. So if something has a very small heat capacity, it becomes hot immediately and it becomes cold immediately. But if it has a large specific heat capacity like this, it takes long time to get hot and long time to get cold. Yeah. So water is very hard to heat and water becomes hot for very long time. Yeah. Everybody got that? So like this. Good. Now I'm going to show one equation here. This is really important and it's the fundamental equation for all thermodynamics. So how much heat energy somebody absorbs? So it's calculated by Q is equals to mass of that substance, specific capacity of that material, and what was the temperature after heating, and what is the temperature before heating. So by this equation, we can easily measure the amount of heat. It's actually very hard to measure the heat. We cannot measure the heat simple way. So we cannot measure this Q. You see that? So heat cannot be measured that easily. Actually heat cannot be measured. So heat cannot be measured. Can't be measured. This guy can't be measured, but we can say how much heat it changes. For example, I can't measure your knowledge, right? How much knowledge you have, I don't know, but I can know that how much knowledge I transfer to you, right? So the Chem 105, how many notes I have here, that much knowledge I transfer you. Make sense? So So we can just talk about the transfer of the knowledge or transfer of the heat here. Make sense? So only transfer of the heat can be measured. So heat cannot be measured. Transfer of the heat can be measured. Yeah. So let's talk about this one. So I have water here. So let's say I have 5 gram water here. I have 5 gram water here, right? I have 5 gram water, and I already told you specific heat capacity of water C is 4.2 joule per Kelvin per gram, like this, per Kelvin per gram, or it can be degree centigrade also. Kelvin and degree centigrade is same thing. Degree centigrade is like that. So C is always, we know in the book, a lot of people have already measured the specific capacity, and they give this value in the book. So the mass is 5 grams. So I have 5 gram water here in the beaker. So I put this in oven, and before turning the oven there, I measure the temperature of this guy, and it is 21 degrees centigrade. So I have at the initial temperature I have T1 is 21 degrees centigrade. Now I turn on this oven and I start heating and heating and heating and heating, and maybe after 10 minutes, 20 minutes heating, the temperature becomes, let's say, 80 degrees centigrade, like that. Make sense? If you got that, what I'm saying? 80 degrees centigrade. So T2 becomes 80 degrees centigrade. So how much heat is transferred from heater to oven in this process? So I'm going to write it here. So heat transfer is Q. So how much mass? The mass of the water I have is 5 gram, and specific heat capacity of this water is 4.2. And then T2, I heat up to 80 degrees centigrade, and initially this temperature was 21 degrees centigrade here. So this much heat is transferred. You see that? So this much heat is transferred from heater to this water. Make sense? So how much heat is there in this beaker? I cannot tell. Make sense? I'm just calculating how much heat I could transfer from heater to the oven to the water, right? But how much heat this water has, I don't know, right? How much knowledge you have, I don't know. Maybe you have physics, you have geology, geography, environmental science, geometry. I don't know what you have studied already, right? But I can definitely say that how much knowledge I'm transferring to you, right? So the chem 105, I'm starting from 1 to I go up to 9. So that much knowledge I transfer. So like that. Make sense? So we don't know how much heat is with something. Nobody knows. So we only know how much heat we transfer from one place to another place during the process. Yeah. So that much. So just calculate it. Put in the calculator. 5 multiplied by 4.2. 80 minus 21 is 59. This is 59. And then 5, 4, 20, 20 and 5, approximately 100 joule of heat energy is transferred from here to here. Just put in calculator, yeah? I just did the mentally calculate there, but that's about 100 joule. 5 multiplied by 4 is 20, 20 multiplied by, no, not 5, it is 5 gram, right? 5. So approximately 100 joule of heat energy is transferred from heater to water. Everybody got that? Simple. So you need to know 3 things: mass, specific capacity of that material, and initial temperature you need to measure with thermometer, and final temperature after you heat, how much is the temperature, and then you just plug those numbers there, and that much heat you transfer. Got it? Like that. Good. So this is very, very important equation, and it will be in exam, yeah? So delta T, sometimes it is written here is don't get confused with this one. Q is equals to MC delta T. It is writing like that. So it's same thing. MC T2 minus T1. So this delta T is basically T2 minus T1. Yeah. Good. Which is final, and that's initial. So. So I have one problem here in already. So we are about 5 there. So I'm going to use one equation here. So I have one problem. If 50 gram water is warm, so I have, they're saying, so this is a water here. We have 50 gram water here. So mass is 50 gram water here. And then the initial temperature. So they have the thermometer they put here. And initially it is showing 25.3 degrees centigrade. And they put this in oven. And they heat. And after several minutes, the temperature becomes 33.2 and 7 degrees centigrade. So how much heat energy transfer from here to here during this process? So simple. So Q is equals to the heat transfer. Q is equals to from here to here is equals to MC T2 minus T1. So M is 50 gram, C is 4.2 for water, right? So this is water, and for water, that's constant value is 4.2, and T2 is 33.7, and minus T1 is 25.3. And then you just plug this number in calculator, and whatever that comes, that means joule. Yeah. So this is, comes about 1757.3 joule. Yeah. So this water is absorbing heat or losing it? It's absorbing, right? So heat is going from here to here, right? Yes, water is absorbing it, right? So that's a plus sign. So we just give the plus sign. But you really don't have to worry about that sign there, yeah, because it is absorbing heat, becoming hot. Good. So the specific heat capacity of water is 4.184, or you can write 4.2. It's the same thing, yeah. You can write 4.2 or 4.184. It's the same thing. Calculator gives the answer, right? Got it? So I just this 4.2. I'm just rounding that 4.18 to 4.2. Good. You can write 4.182, 4.2. It doesn't matter. 4.184. So approximately 4. Good. So same thing. So there are a lot of other problem here. Same thing. I'm talking about exactly same thing. So let's look here some problem. Now this one is how much heat is needed to warm 250 gram of water from 22 to 98 degrees centigrade, the specific capacity of the same thing. Yeah. So I'm not repeating the same problem here. So I'm going to show one problem here. This is in the lecture 2, chapter 5, lecture 2, and mixing two things. No, it's here, one more problem here. So I'm going to show you this one here first. So I'm in the slide number 1, problem number 2. Yeah. So what is the specific capacity of the silicon? So it is saying that. So this is not water now. So this is a silicon. So they have some silicon here, not water. So this is silicon here. If it takes, so they put this in heater here, and the temperature at the beginning was. So how much mass? So mass of the silicon here is 45 gram, and maybe the temperature of this guy at the beginning was 21 degrees centigrade, and they heat it, and the temperature changed by 6 degrees centigrade. So when at the beginning was 21, if the temperature changed by 6 degrees centigrade, how much is the temperature? So 21, 27, right? 27 degrees centigrade. So that's what it is saying. Make sense? The temperature changed by 6 degrees centigrade means if the temperature at the beginning was 21, the after heating temperature becomes 27, right? By 6 degrees centigrade. See here, 7 minus 1 is 6, right? 2 minus 2 is 7. So 6 degrees centigrade. So what is the specific heat capacity? So they are saying, so how much heat it is up? They are giving Q is equals to 192 joule. So like that. So let's put this one. Q is equals to MC T2 minus T1. This is our formula. So Q, how much heat is transferred from here to here? They are already giving in joule. 192 here, 192. M is 45. C is, I don't know. They are asking us to calculate T2 minus T1. They are saying the temperature increased by 6 degrees centigrade. Like that. So 6 here. So I want to just cancel this one and this one and put here 45 and 6 here. So that's 192 divided by 45, 6 is equals to C. Make sense? So I just pull this and this factor down here. Everyone got that? Good. It's just can I do this? So this is how we do it, right? This goes down there, right? And then the value of C is this. So how much it comes there? 0.711 joule per gram per degree centigrade. Good. Already, so do another one. So this one is a mixing. So, so this problem is a mixing things at different temperature. Of 145 gram sample of copper metal at 100 degrees centigrade is placed in 250 gram of water. So let's look here. So this is a copper. So this is a copper piece, and the mass of, let's write the mass of this guy is M1, which is 145 gram. This is copper, yeah. So this is copper, COPPR, copper, and then mass is 145 gram. And I measure the temperature of this guy by putting the thermometer here, the T1. The temperature of this guy is 100 degrees centigrade. 100 degrees centigrade here, right? 100 degrees centigrade. Now, I have water here. So I have water here. So two things. I have two things here. So I have water here, and water is 250 grams. So I have how much water here? So I write M2. That's 250 gram here. So I take some water here. That's 250 gram, and I measure the temperature 25 degrees centigrade. So this is 25 degrees centigrade. So I write, let's say this is a T2, or I can write anything. So the T2 is, so the temperature here, T2 is equals to 25 degrees centigrade, like that, yeah? So, all right, so look here. So this is a copper, this is water. So they have different temperatures. So you got what I'm saying, right? So I have a copper piece there, and the temperature is 100 degrees centigrade, and mass of that copper is 145 gram. And I have in another beaker, I have 250 gram mass, and the temperature of water is 25 degrees centigrade, right? The two things, I have two separate things at two different temperatures, right? Now what I do is I'm going to throw this here to here, yeah? So I'm going to throw that hot body to the cold body here, and it looks like this. So this is water, so like that, and then I throw that piece of copper here, and I have thermometer already here. So the temperature of this mixture become how much? 28.8. The temperature of the water in the calorimeter become, when the system is equal. So this becomes 28.8 degrees centigrade. That's a problem, yeah. That's what it is saying. Makes sense? So you have basically, you have a copper there. You measure the mass of this copper piece, 145 gram. You measure the temperature of this copper piece with the thermometer, it's 100 degrees centigrade. Here you have water. You measure the mass of that water, 250 gram, and you measure the temperature of this water with the thermometer, 25 degrees centigrade. So then you just take this and throw it here, and it looks like this. When you throw this here, it looks like this, and you wait for a while, and the temperature rises to 28.8 degrees centigrade. Make sense? Just like that. So how much? This is here. So this is very hot. This is very hot, right? 100 degrees centigrade. This is very cold, 25 degrees centigrade, right? This temperature is somewhere in middle, right? Make sense? So hot always lose the heat, cold always gain the heat. So how much heat it lost? So let's calculate the heat lost by this one. So heat lost by this one is always like this. Q is equals to MC T2 minus the T1, like that, right? Heat lost, this guy lost the heat to this one here. So how much heat it lost? So that is M is 145, and C is copper. What is the copper value there? The value of the copper is 0.385. So this is 0.385, and what was the temperature it had at the beginning? The temperature it had was 100 degrees centigrade, 100 degrees centigrade. And what is the final temperature after mixing? That's the 28.8. So that much heat it lost. Make sense? You got it? Yes? That much amount of heat that copper piece lost, right? Because at the beginning, it has 100 degrees centigrade. At the end, it has 28 points. So whole system is 28.8, means this guy is also 28.8, right? So that much heat that guy lost. So now you have that. what should we calculate here? We need to calculate is what is the specific? What is the specific heat of copper? Actually, it was not given. I'm not writing this one here. So they were asking to calculate specific heat capacity of the copper. So I'm just writing it here. Yeah. So mistakenly, I put that 0.385 here. Just don't take that 385 there, right? So we need to calculate C later. So here, how much heat? Look at, so this system was at 25. Now its temperature from here increased to 28.8, right? Make sense? Everybody got that? So how much heat it absorbs? So it's basically Q is equals to MC T2 minus T1. Look here. So you can write whatever you like here. So one is, this is T1, this is T2, this is T2, this is T1. Doesn't matter, whatever you want. So M is 250. C of water, I know that's 4.2. And then T2, let's write 28.8, 28.8. And then T1, or you can write 25, whatever you want to write. So minus 25, right? Basically, I'm just subtracting from here to here, or one temperature to another temperature here. I'm not doing anything. Make sense? You got that? So in this process, this guy become cold. So from 100 to 28. And in this process, this guy become hot from 25 to 28.8, right? So one is losing heat, another is getting that heat. So losing heat and gaining heat are equal, right? So for example, I have this pen, I just give you this pen. So I lose my pen and you get this pen. So losing and gaining is always equal. Make sense? Everyone got that? So if I lose $5, you take $5, right? So losing and gaining are same. Or if you lose $5 and I pick that $5, I gain the heat and you lose $5. So quantity is same. Make sense? So I'm just equating this number, whatever number it comes here. So what number it comes here, I don't know. So you can just put here, and if any negative sign comes there, just disregard that negative sign. Yeah. So if any negative sign comes, just disregard that negative sign. Let's look here. So how? So I think I have already done calculation here. So whatever number it comes here. So I was doing just one step there. So here I did a little bit different way. So let's do this one. So this is 250 multiply 4.2. Then I put this bracket in 28.8 minus 25. So this number comes to be 3,990. So 3,990 here, right? Make sense? So that means so what number comes here? So 145, 100 minus 28. So that comes to be, so let's calculate that one. 100 minus 28.8. So 71.5 multiplied by 145. So I got 10,324. 10,324, and I have C here. Make sense? Everybody got that? So this guy in this process lost that much heat, and this guy in this process obtained that much heat, and this heat must be equal, because one lost heat and the same amount of heat is gained by the another guy, the water, right? So let's make them equal. So so this one 10324C is equals to this one 3990. So here, so this is multiply here. So this factor going to go down here. So C is equals to 3990 divided by 10324. So whatever number comes here, so that is so 245. So 24. So approximately 0.3, I think. So that's 3990 divided by 10, 324, so approximately 0.386. Got that? So that much is the specific capacity of that copper. Yeah. Okay. So you understand the problem, right? So we need to understand the problem first. What is going on there, right? Good. So let's look there. Now that here. So if the most important thing here to remember is during this calculation, if you get minus sign, just disregard that. So specific capacity, for example, mass cannot be negative. Mass cannot be negative. So if you get minus sign with the mass during the calculation, you just say, oh, mass cannot be negative, and just disregard that minus sign. Make sense? And if you are calculating the specific capacity and you somehow you get minus sign, just disregard that. Specific capacity cannot be minus. Yeah. Can I say my mass is minus 55 kg? I cannot, right? So suppose I calculated my mass and I say, oh, I got my mass is minus 55 kg. That is not possible. So some reason I might get that minus during the calculation from somewhere, right? So I just disregard that minus sign. Yeah. So see, it cannot be minus. And then, but temperature can be negative, right? Temperature can be minus 22 degrees centigrade. Temperature can be plus 50 degrees centigrade. So when comes the temperature, if we are doing the temperature calculation, we cannot disregard the minus sign. Yeah, we have three things: mass, C, or Q, T, whatever. Q also, you don't have to worry about the Q also. So don't worry about Q. So it may come to minus, it may come to plus. Don't worry about this. Yeah. So the temperature, when we are calculating temperature, we must understand something there. Yeah. So let's do that. If there is a temperature calculation problem here. So I think mixing two things, you can do these two things there. It's the same problem there. You can do that one. So all problem are just using the QAMC T2 minus T1, and you just have to calculate C. You just practice those. Mixing two things. So all problem are actually the same repetition. So let's look one problem here. So I'm in the slide number 6, and it is saying a series of equal mass of sample of 5 material listed in the table were brought from room temperature to 100 degrees centigrade. So here is an aluminum, here is a Pyrex glass, and here is iron, lead, and water, liquid water. So there are these things, and a series of equal mass of sample. So first they did aluminum, so they put aluminum. So let's say they put 50 gram aluminum here. So this is aluminum, and another they put Pyrex glass here. So this is Pyrex glass, and 50 gram here. So they put 50 gram, and iron in another glass they put 50 gram iron. Same, you can write any mass, same amount. Another they have lead, 50 gram, equal mass, 50 gram. And in water, another they put water, and it's again 50 gram. Every material is 50 gram. They put in all these beaker. Make sense? So that's what they are saying. A series of equal mass, equal 50 gram, 50 gram, 50 gram, right? Table are brought from room temperature to 100 degrees centigrade. Room temperature is 25 degrees centigrade. Room temperature means in this room now is about 25 degrees centigrade. So it's a 25. At the beginning, 25. So all this is 25. Now they hit this one and become 100. They hit this one and become 100. They hit this one and become 100. They want hit this one 100. They hit this one and become 100. Make sense? You understood the problem, right? So they took 5 material, same amount, 50 gram in 5 beaker, and the room temperature, every material was 25 degrees centigrade, and they start to hit from 25 to 100 degrees centigrade. And which one would get, which sample required the least amount of the energy? So look here, the least amount of the energy is, which has the least amount of the specific capacity, that is the least amount of the energy. So here specific capacity of lead is 0.128. So the least specific capacity is with the lead, and that is 0.128. So if they take 1 gram of this guy and hit from 21 degrees centigrade to 21, 22, this will take 0.128 joule, right? So this guy, it becomes hot immediately. Make sense? Whoever has the least specific capacity, that becomes very fast hot, and it cannot absorb much heat, right? Everyone got that? So this absorb 0.128. A lead would, iron would take 0.44. This one 0.44. Aluminum would take 0.903. 903 for 1 degree centigrade change. Pyrex glass would take 0.75, and then water would take 4.18. Look here. So who would take, if we heat this material with the equal temperature from 25 to 100? So this guy would take a lot of heat, right? Because this has a large specific capacity. Make sense? So whoever has a large specific capacity, that absorbs a lot of heat. Make sense? Whoever has the least specific capacity, that takes a small amount of heat. That means that, yeah. So the question is, which sample requires the least amount of heat energy to reach the final temperature? So the lead will take the least amount of heat to reach the final temperature. And which material takes the highest amount of the heat to reach to the final temperature? That's 100 degrees centigrade. That's water, because water has the large specific capacity. Make sense? So whoever has the large specific capacity, they need really a large amount of heat energy. We just keep heating and heating and heating and heating, and it never becomes hot. Yeah, it takes long time to heat water, right? But if you want to heat lead, immediately it becomes hot. Pyrex glass, it's a little bit harder to heat than lead. The aluminum, a little bit harder. This water really takes a lot of energy to heat. Yeah. Make sense? So like that, yeah. Alrighty, so yeah, probably we stop here and we will continue after spring break for some problem of mixing, and yeah, these are an important problem, yeah. So chemistry is really important, yeah. Like you go to the energy industry to work, Joule, whatever. Alrighty, everyone, have a good spring break. I'm enjoying this warm weather. It's too cold here.